We will start from last class. What we left is we looked at some of the problems that are associated with the resistance spot weld, right. Suppose if you have a dissimilar thicknesses, right. So, if a material has a very high thermal conductivity or electrical conductivity, and if you are using in a case where thicknesses are different, right. So, suppose if the material has a different conductivity or the same conductivity which is higher, and you are welding two sheets, right. If a material has higher conductivity, so obviously the mass of the larger thickness would conduct the heat much more effectively. That means that you may not make the welds at all in the thicker sections. You will end up making weld only at the thinner sections, isn't it? Because heat is contained. There is no mass effect to transfer the heat effectively from the thick section welds sheets. Okay. On the other hand, or in contrary, suppose if your material has a low conductivity, okay, then what will happen? The heat is contained, right. So, it is not effectively contained, and whereas in this case material the heat can be conducted because of so proximity to weld. So, material has a low conductivity, obviously you will end up making the welds only at the thicker sections. So, these are some problems you may expect when you are doing dissimilar thicknesses, and the same effect can also be seen if you are welding a similar thicknesses material with different composition. Okay, the same effect you also see. So, suppose one material has a high conductivity whereas another material has low conductivity. So, obviously, so you will end up making weld only if the material has a low conductivity, isn't it, right. So, because the heat can be conducted in the other side, and these effects are very predominant and when you are doing dissimilar welding, whether dissimilar thicknesses or dissimilar materials. So, these you will always have a problem when in a commercial production where thicknesses may not be same all the time. So, you have to look at the material composition. If the similar material, how we can optimize it. One way of optimizing it is change the electron diameter accordingly, so that you reduce the you optimize the thermal conduction to make the welds in the same size in both top and bottom plates, right. Or you can also change the electrode material accordingly. So, one electrode can be made into high conductivity copper and other one with the alloyed copper, right. So, that you can contain the heat. It is clear. Okay. So, these are some of the problems. The other problems we looked at is the shunt effect, right. Shunt effect happens when you place a weld very close to each other. So, the distance between two L is very critical. So, if you look at the cross section of the resistance spot weld, okay. So, if you have one weld, you placing it here, another weld if you are placing it very close to each other, then what will happen when the electrons, when they travel from the electrode to the other electrode, and they would always find the least resistance path, right. So, instead of traveling, and it may also go through the weld which is already made. So, obviously instead of making a weld here, you will end up heating the weld which you already made. Okay, the shunt effect is very common. So, that is why the distance S between the weld is very critical. So, we learn to identify the distance between the weld, what is the critical level, so that we can minimize the shunt effect, right. So, the other effect we saw was the Peltier effect, right. Peltier effect. So, it is opposite to the Seebeck effect, right. And in resistance spot welding, you always have dissimilar junctions, right. So, if you have a copper electrode and then you are welding a steel sheets, okay, two sheet steel shields, right. Okay. So, you always have some junctions. For example, you have a one dissimilar junction here and another one over there, isn't it. So, here the iron copper junction is iron junction, right. So, suppose if you are passing in a DC current and EMF, right. So, between two positive and negative terminals where the electrons will travel from the cathode to anode, and when you have a dissimilar junction and you are passing an EMF, the dissimilar junction would never be in same temperature. Okay, so, that is opposite of Seebeck effect. So, Seebeck effect says that when you immerse in a two dissimilar junctions in a two different temperatures, there is an EMF generated, isn't it? That is what Seebeck effect. So, the same concept would also work. You have a dissimilar junction, you pass an EMF, and these two dissimilar junctions would never be in same temperature, right? One will be hot and one will be cold. So, that is what can happen when you are using DC current, direct current to weld in resistance spot welding, and you have an EMF sent through at dissimilar junctions. So, obviously, these junctions may never be in same temperatures. So, obviously, one end you may end up heating it more than the other end. So, the weld may not be uniform. You may always have one dissimilar heating, end up changing the weld nugget size heterogeneously. Okay. So, this Peltier effect is common when you are using DC current to weld, direct current to weld. Okay. So, that is why in most of the cases in resistance spot welding, we always use alternating current, where the polarity is switched, right, in a cycle. So, in alternating current polarity is switched. So, we can overcome the effect of dissimilar junctions being hot and cold, right. It is clear. So, these are the quite common problems we see regularly. That is what we discussed in last class, and we will move on to the next section to see the other variants of resistance welding. Okay, this is clear, right? Shunt effect, shunting current, and then the Peltier effect, right. So, you would expect the electrode erosion, very severe electrode erosion, and because of the dissimilar heating. Okay. And then this class we will move on to the next unit in this section, and which are actually derivatives of the resistance heating process. So, we use various modifications of Joule heating, and then we also add extra material so that the joint geometry as well as joint property can be improved significantly, and we can also extend the range of materials that can be welded by resistance heating. So, one such method is resistance brazing. Resistance brazing, it is the concept, the heat generation mechanism, the physics is the same as the resistance spot welding. So, where we have a two overlapping joints made using a two electrode by passing alternating current. Okay, Joule heating is carried out by contact resistance, and then you can do nugget formation. In most of the cases, as we explained, the material should be compatible. Okay, so if you look at if you recall the table I showed you, A, B, B, the compatibility of the material. Suppose if you are welding aluminum to stainless steel, it is E. It is very difficult to weld, right, because of the cracking that is actually happening when you are doing this dissimilar weldings. Okay, because resistance spot welding, you always have a load acting on it and the weld joint. So, in order to overcome that problem, so we can also add extra filler material in between the overlapping sheets, right. That is a possibility, and this filler material can be compatible with both sheets you are welding, right. So, if you are using a filler material and this filler material can melt, you can make a joint between the two faying interfaces. Like, so, in this setup it is the same. For example, you have an electrode and the overlapped joint, but before making overlapping we keep some filler material in between these joints. Okay. So, most of the cases the fillers are the flux coated wires, right. So, that it can act as a butter layer. So, we generally call it as a butter layer, just to add butter to a toast, so that it goes in to your stomach without any problem, isn't it, right. So, we also add some butter layer in between the faying interfaces as a filler, and these fillers can be flux coated mostly silver or low melting constituents, solder alloys, or sometimes even we can also use a similar material, sheets of for example, in steel aluminum welding you can place a nickel. Okay. I am just giving an example, right. So, this filler can be placed in between the sheets, and then you are basically creating more interfaces, more contact resistance. So, you will end up melting the filler, and the filler can wet the surfaces, and then it can also diffuse to the surfaces, and this filler can be compatible for both the sheets. okay, right. And by doing so, so you end up making a joint when the filler solidifies, and then now you can also make it use it for a large parts, because the filler can melt and make a complete seam, for example, a longitudinal section. Whereas in spot welding, these are done in a different geometries, different diameter. So if you are keeping a long filler and then you use a long electrode and melt it and make a very good joint. Okay, you need not melt the interfaces of the base material. You just melt the filler and let the filler solidify, and then while solidification, now it can make a complete weld across the interface. Okay, it can be used for smaller parts, it can be the bigger parts, right. So in the bigger parts, in this process generally we use the graphite electrodes. Say for example here, the graphite electrode, right, and then we have a large workpieces and the filler is kept in between, and the electrodes are pressed to each other and then apply a load, pass the current, and this flux melts and then makes the joint complete, right. In this process, in most of the cases we do not completely melt the base material. So the filler melts and then we may end up melting at the interface, right, and then the diffusion would complete the weld joint. So that is why this process is mostly known as resistance brazing, because the workpiece is not molten completely, right, isn't it. So filler generally we use is low melting alloys, say for example steels, stainless steels, heat resistance alloys, copper. Generally we use the silver type, the braces. The melting point of the silver based solders are slightly higher temperature. So you need to use more current in order to identify, in order to melt the fillers so that you can deposit, right. But we replace lead with the silver, and then yeah, the carcinogenic problems can be overcome. So the silver paste or a silver filler with the flux coated silver wires are very commonly used for brazing applications, brazing and soldering applications. And these silver based solders and braces, they can also withstand higher temperatures because melting point is slightly higher than lead based solders. So for brazing applications, we commonly use silver fillers in order to keep the interfaces like I showed you molten, and then make a joint, right. So that is why now modern the filler wires for the solders and braces are slightly expensive because of the use of silver, right. So for a good brazing, so we can also use a silver paste. Otherwise we can also think about copper alloys. So copper alloys melt in a similar temperature. Now we can also bring down the melting point of copper by adding phosphorus. Okay, so the copper phosphorus system, they are also used for brazing applications. You can develop a filler with the copper alloy, place it, and then apply current and load. The filler melts and make a joint. Okay, so the aluminum alloys, aluminum silicon filler is very commonly used, not only for welding, also for brazing applications. And if you choose an aluminum 12% silicon, so why aluminum 12% silicon? Eutectic composition. So the melting point will be much lower than aluminum alloys, the other aluminum compositions. Okay, so you can use aluminum silicon filler, so the melting point can be lower, and you can heat it up until the melting point of the filler, and then you can make a brace joint. It's clear? Any questions so far? Good. So we will move on to the subsequent to resistance brazing and resistance seam welding. And the resistance seam welding, okay. So instead of using a single point electrode, we use a roller electrodes. Okay. So roller electrodes, no, it is the concept, everything is the same. Okay. So instead of using a single point contact, we will have a wheel which acts as an electrode. Okay. and the material which is to be welded, it is actually sent to these rollers, okay, and then you pass a current and load is applied, like the same way what you do it in a resistance spot welding. Only here is because material is continuously sent through the rotating rolls, and you will end up heating the interface continuously, okay, like a seam, and then you will end up making a continuous seam welding through the length of the sheet which is actually fed to the rollers, okay. And this is very commonly used for welding long sections, long and thin sections. For example, the most common application of this roller resistance seam welding is to make fences, okay, or corrugated sheets, roofs, right. So, have you seen the roofs of a corrugated sheets, something like this, right? Okay. So, these sheets sometimes may contain that couple of the two sheets or 4 plies, 2 plies they call it, okay. So, they may also have different sections, and these are all welded using resistance seam welding, okay. Similarly, the nets, window frames, okay. So, if you have a long fences made of flat sheets, you can buy them. So, these kind of corrugated sheets, and those are all made using resistance seam welding, where you will have rotating electrodes, and then the flat sheet is sent through the electrode, and you may also have additional work rolls which would actually bend or change the shape of the sheets, and then once it fed to the electrode rolls, and then you pass a current. So, obviously, when the sheet is moved towards the other side, then you may end up melting the interface continuously, right. It is clear. Then you will make a continuous seam welding, and this process is also commonly used for pipe making or tube making, okay. So, tube making also very commonly used. So, instead of making in a flat rolls, you may also have a bending rolls, okay. The bending roll would bend the sheet, and then using an induction coil, you may also have an current passed at the interface, and contact resistance subsequently would melt and then make a joint, okay. So, the seam welded tubes and pipes are also made using a resistance seam welding, and if you look at it, it can be circular configuration or a longitudinal configuration. So, whereas in a circular configuration, you can make a continuous seam of weld, isn't it. So, if it is fed rotated like this, you can send the continuous sheets along these rolls, and you can make as long as possible the seams, isn't it. So, the sheets of the alloys can be overlapped and then send it through the roll, and then the weld can be made continuously, okay. Or it can also be made into in a reciprocal way. For example, and the wheels can be rotated and then it can be welded, okay, and subsequently we can also rotate in other direction, and you can also make subsequent welds, right. So, this is a circular machine, and this is longitudinal machines, where the control the motion control can be reciprocated in such a way that we can also do an alternative way, right. So, that is also possible. So, objective of this is to extend the resistance spot welding into a much longer the weld with a seam, like seam means a continuous longitudinal weld made over a large dimensions. Yes, it is clear. Okay. So, these are also commonly used for making engineering applications, mainly on thin sheets, and if you want to build a component out of thin sheet which are very long, and the seam welding can be used. So, some of the variants of resistance seam welding, for example, lap seam welding I showed you already in the first the image of resistance seam welding. And lap seam welding, so basically you have an overlap joint, and this overlap joint the sheet is sent in between the rolls, and the rolls are electrodes. So, when the electrodes, when the rolls pinch the sheets, so obviously it is at a given time t, it is like a spot weld, isn't it. So, at a given time it is like a spot weld, where you make a weld, but it is actually continuously moved, Okay. So, you melt it and then it continuously moved, and subsequently the other area will come into contact in the electrical circuit with least resistance direction for the electrons, and you will end up heating by the contact resistance of the interface, and then you will make continuous stream. Yes, it is clear? Okay. And then no, we can also add the advantage of mechanical forces that we may also subject these interfaces to enhance the weld quality, okay, or weld metal properties. So, for example, in this case this mesh shim. So, mesh shim is done, we will have instead of overlapping. So, you may also have a sort of a fillet configuration, and then you keep the sufficient force in such a way that you may also have a mashing effect once you heat up the liquid, the interface above the melting point. Okay. So, you can also apply a mashing, so that you may end up creating a joint sort of close to the butt weld. Okay. So, butt weld is, so basically you have a joint something like this, is not it. So, when you have, we can make a weld, so you will have a weld made something like this, is not it. So, similar configuration you may also achieve in mesh shim weld. So, where you keep a material in slightly in a fillet configuration, and then you have an electrode. Okay, we will take this off. So, top electrode and bottom electrode. So, push it. Okay. So, once they are in contact with the workpiece, you pass the current, you melt the interface, and this becomes really softened. Okay, and then apply a mashing load in such a way that and these two becomes one with a weld in between. Okay. So, this is similar to what you do in a butt weld configuration, right, and this is known as a mesh shim welding, right, and you may also have a finish welding. So, in this case, so this is like it's sort of you have an overlap as well as a shearing action takes place during welding. So, one of the electrode is slightly tapered. Okay. So, this case, is not it, and then you again the process is the same as resistance spot welding. You bring the electrode together, and then let the contact resistance heat up the interface, and upon achieving required weld dimensions, the melt pool, and then you do a mashing action, so that so you take away the excess material and then shear it out you as a flash, right. So, advantage of this process over this process is, in this case the edge preparation is not really necessary, is not it, right. So, in this case, so you will have to make sure that the edges are prepared well, and if it is not oxidized, and it will end up trapping inside the melt pool, is not it, because the flash is not removed, the flash is contained inside the pool. So, the edge preparation should be very good in such a way that the surface, the oxides or any other contaminant, those are removed properly in mesh shim welding. So, whereas in a metal finish welding, the electrode is kept slightly chamfered in such a way that, so when you are doing welding, the excess, the surface, it is actually is coming out as a flash. So, the surface preparedness, the efforts can be minimized in metal finish welding, right, because the pre surface is removed as a flash. And this process or this methodology is also commonly used in various resistance based processes. Okay. So, we will move on to the other processes where we can also look at it.